wonderful term. Thank you also to the people who organized the whole trimester for doing that. You're great. Keep doing good stuff. Okay, so what's the goal of this talk? So I have a goal and a dream. We'll achieve the goal, but so the dream is still a dream. So the goal is to attach some differential structures. In this case, it would be tangent bundles. To many diamonds arising, or whatever you want to mean by this, but naturally in the study of rigid dynamic varieties. So I'll be always working over some set of QPs over some non-Archimedean field in characteristics of 0. Okay, in mixed characteristics, right? And so that's the goal. And why do I want to do this? Well, the dream, as that's my title, is if you have such differential structures, then you could sort of want to go back and use them to sort of prove things as sort of an extra tool to prove things about the diamond. So use this extra structure to prove something about the diamond. So some components extra structure differential, it calls whatever we're proving topological. Underlying that. Okay. Well, there's an example of this that motivates everything. So this prototypical example. This is the Farg-Schulze Jacobian criterion. So you'd think, for a protocol example, I'd want to go into a lot of detail and sort of write down carefully what this says, but I'm not going to do that actually, because there's somehow the spirit of this talk is we're looking for sort of examples that almost somehow will live in a simpler world, or at least a more sort of naturally geometric world for my head. But in the Farg-Schulze Jacobian criterion, what it says is if you construct a diamond as some moduli space of sections of sort of some smooth adic space over a Farg-Fontaine curve, well, then there's a natural way to attach sort of tangent bundles to such a thing, sort of using sort of some naive, using sort of maybe naive guesses about what the tangent bundle sort of section should be coming from classical geometry. And then you put some criterion on these tangent bundles, and that criterion sort of forces, like, what Farg-Schulze proves that criterion on these tangent bundles tells you your diamond is cohomologically smooth. So you have sort of a diamond over some other diamond and is sort of constructed as a moduli section of the relative Farg-Fontaine curve sort of over that diamond. It gives you a way to tell that morphism is cohomologically smooth. So I want to emphasize one thing, which is, I'll write you that example. The tangent bundles are not intrinsic to the diamond in any way. The tangent bundles come from the way you construct the diamond. So secretly, when you construct that diamond, you're constructing this specific way where you have some extra information floating around, and you sort of use that extra information to sort of call something a tangent bundle, but there's in no way intrinsic to the diamond. And you can only see that in sort of a much simpler example. So here's sort of one of the key issues. So the issue, first thing, is not a issue. So, and diamonds are very, very nice in the sense that sort of they're stable under all sorts of operations. So if you want to sort of do math with rigid analytic varieties, you want to study rigid analytic varieties, and somehow, like, you're just studying rigid analytic varieties, you can sort of do natural things that very quickly leave the world of rigid analytic varieties. You could try to take like a limit of a tower of finite Hall covers. It's no longer a rigid analytic variety, it is still a diamond. It's not limit exists in diamonds. This is basically why I want to work in diamonds. I'm interested in rigid analytic varieties, but I want sort of some world where I can do operations like that. Like I want to take quotients, I want to pass the limits and so on. So they're very nice in the sense that they are stable under natural operations. for example, like geometric operations. But they're sort of not always very analytic. And so here, I mean, of course, diamonds are sort of some functors of a perfectoid space, or the perfectoid spaces are defined in some sort of version of analytic geometry. So in that sense, of course, they are analytic, but they're not analytic in sort of like, I don't know, like first year graduate student sense where you have like sort of power series and sort of complex analysis. So in that sense, diamonds are not very analytic. And you can see that already in the simplest example. So e.g., if I look at sort of VP, so this is a cofinite set or cofinite group, and I can sort of naturally equip that with the structure of a diamond over the diamond QP. So I'll always sort of be working with diamonds over a specific non-Archimedean extension of QP.
CB, you're just thinking of it as a topological space? Or?
Yeah, this is a topological space. I mean, so somehow that's, you know, yes, just for now, this is a topological space. And so, well, as a diamond, and if diamonds have underlying topological spaces, that's one of the ways in which they're a nice geometric category. And for this, the underlying topological space is the ZP again. And then if I have a diamond over a split QP, then I have sort of a structure sheaf on it. So sort of the structure sheaf, which sort of descends an open set to the map. Well, any open set underlies a subdiamond, and then I can take maps from that subdiamond to sort of the A1 diamonds, like what you really naively mean by functions. So A1 over QP. And the structure sheaf for this diamond over QP. This is a sheaf on this topological space. Is the sheaf of continuous functions. On ZP. So, and in particular, you can't tell ZP and ZP squared apart just by sort of using sort of this diamond structure. Of course, you can sort of guess sort of there are other sort of sheaths you might want to try and put on here that would be more analytic, but the one you get for free from a diamond is sort of not very analytic. So that's sort of why we have to sort of have some extra structure in order to get tangent space in sort of absolute generality. That's sort of, and then sort of let me say, but I told you sort of we have a way to do this. I told you we have this Farad-Schultz Jacobian criterion. And so some of the main problem with life, as I've sort of explained life to you so far, is that most diamonds built from the dynamic varieties, sort of by doing these natural sort of constructions that work well in the category of diamonds, and you can construct these diamonds, but there's no way to realize these using the Farad-Schultz Jacobian criterion. So sort of cannot, obviously, we realize as sort of something where the Jacobian criterion applies. So somehow this talk would be over if the Jacobian criterion sort of applied sort of everything. We would just use that to define our tangent bundles and sort of know sort of why they were what they were. But the issue is just, and it works for some things, it works great for the things that show up, and it works great for some things that sort of, it does work great for some sort of things that show up naturally in more general geometry, but it doesn't work for everything. So here is sort of like the first example where it doesn't quite work. I'd probably use, I'm not used to, this is how I'm supposed to erase the board, is this right? And maybe while I'm erasing the board, I'll ask if there are any questions so far. So here's sort of an example of something where you cannot use the Jacobian criterion. So, let S over QP the finite level modular curve. And I'll write E over S, so U as a Reginac variety, and I'll write E over S for the universal family of elliptic curves. Okay, and then I'm going to let S sub E, so this E stands for the identity element in a group. The group is GL2ZP. And that in a second. So this is the sheaf of isomorphisms from ZP squared to the tape module of E. So the chaotic tape module to E sort of form a ZP local system. It's locally isomorphic to ZP squared, and it's taking the sheaf of isomorphisms. This, in other words, this is just the infinite level modular curve. That's E mapping down to S. And this is a active GL2ZP. The GL2ZP torser. So just the infinite level modular curve over S, and then, well, one fun thing you get up here is the Hodge-Tate period map. So on this local system of tape modules, you have a filtration after you sort of tensor with O hat or O, or depending, but sort of you get local system tape modules. So you get a filtration on this, and you can sort of measure its position against your fixed trivialization, and that's the Hodge-Tate period map. Okay, and so what are these things? When this is somehow a very natural thing to do, well, in many perspectives, but just sort of forgetting all of the arithmetic and sort of number theory, and just like you go back like 50 years, and and you want to study sort of families of varieties by studying some how like filtrations vary on their cohomology. So this is sort of a very, very classical idea. And so this is a normal natural thing. And like down here we have S as a rigid analytic variety. And T1 is a rigid analytic variety. But this thing is not a rigid analytic variety. In fact, it's sort of about as far as you can get from being a rigid analytic variety. It's a perfectoid space. Well, it needs a second. This is a perfectoid space. And so, well, one nice thing about diamonds is sort of when I put sort of rigid analytic varieties inside of diamonds, like, that's actually fully faithful. I mean, so some like smooth rigid analytic varieties sort of embed fully faithful in diamonds over QD. So diamonds do preserve some analyticity. They preserve the analyticity of these things. And so somehow, but anyway, so I know how to sort of do tangent bundles for a rigid analytic variety. So P1 and S sort of both have tangent bundles. Well, as rigid analytic varieties, but I want to sort of really think of that as they're coming from sort of favorite differentials. So standard Taylor differentials gives you sort of a way to sort of talk about tangent bundles on sort of varieties in S and P1. But I mean, this completely fails for any perfectoid space. So not so for FT. So I mean, so in sort of more naive sense, this doesn't work. So naively means you just get 0. You get a trivial sort of bundle for the tangent bundle if you try to use continuous Taylor differentials. And sometimes some of the point is so like the defining property for perfectoid space sort of forces all differentials to be sort of arbitrarily p power divisible by sort of differentials of integral elements. I mean, so somehow sort of when you sort of do any note of continuous derivations, you just get 0. You don't have any continuous derivations on a perfectoid space. Be the same sort of as that's naive thing that I'll talk about later. But I probably won't say enough about it, so let me just say it now. So less naive is sort of you look at the locally analytic vectors that are studied by Lehan and Juan Esteban, Rodriguez Camargo. And for this, we'll actually sort of give you sort of some sort of reasonable sheaf of Kähler differentials, but sort of we'll give you the wrong answer. And it won't give you all the way the wrong answer, it'll give you sort of an approximation of the right answer. So one of my, for people who know what this means, for people who don't know what that means, don't worry about it. For people who know what it means, and one of maybe my goals, we'll see if I actually get there, is to sort of convince you the answer you get here is sort of loses some interesting information that you sort of see a different way. Okay, so
I have a question.
yes.
So Howe has this definition, maybe the definition goes back to Gaber-Amero of cotangent complex, right? What studies them for?
Yeah, I think it should just be zero, but I mean, maybe I don't know is the better answer, but does someone know the answer to this question?
No, I mean, it's not zero.
For a projectile space, it's not zero?
So his paper is on the relationship between period rings, Biederam plus relative and Oberram, and these cotangent complexes and the derived Deram cohomology.
Well, this I don't know. So I mean, maybe this is a good question. Maybe I'm not familiar with the work, so maybe you can tell me about it afterwards. Yeah, but of course, what we'd like is just as sort of naive geometers, we would like to have a tangent space for this infinite level modular curve. We'd like to have a tangent space for this infinite level modular curve, and we would like for the Hodge-Tate period map to be differential. So being a naive geometer, let me just sort of try and make that happen. And let me sort of try and make a tangent bundle. I want the tangent bundle, this infinite level modular curve, and then I sort of want all this map on the finite level rho. That's the map. I want pi Hodge-Tate and rho to be differentiable. Oh, it's sort of not so clear what I should do if I want pi Hodge-Tate to be differentiable. So let me just ignore that. And let me instead try to adjust the question of making rho differentiable, like what sort of my tangent space would look like. So let me sort of talk at sort of, I want to do a tangent bundle, but let me just sort of work at a geometric point and talk about the tangent space at that point. This map has to S. And I'm just going to take a geometric point. So little s at the bottom, and then little s sub e at the top. And I want to sort of compute the tangent space of SE at that point. So I want to sort of compute tangent space of SE. Well, okay, this is a torsor for a p-adic Lie group. I mean, if I sort of live in any just world, I mean, this has to be a submersion. So somehow the first thing I can say is that if I have this derivative of rho, well, this should be a surjection onto the tangent bundle of this point, the tangent space of the image S. So if there's any justice, I can sort of So we construct a reasonable theory, this should be true. And then what should the kernel be? Well, the kernel should be sort of the tangent space of the fiber at that point. Well, I have an orbit map from GL2ZP to SE that sends G to G times, right? So SE times G. So I have this orbit map, and this orbit map sort of induces an isomorphism. GL2ZP sort of, I think, is the diamond over, right, so C in here. So C. Is an isomorphism to the fiber over SE, or that's what it means to be a torus, sort of the back insert realizes in fiber. Okay, and so, well, what that means is I should have, all right, math frac G for the Lie algebra of DL2, CP. And this could be included here as the derivative of the orbit map, so X, the identity element in GL2. That should sort of map in here, it should be exactly the kernel of this. So, good. So in this, I claim, is sort of some reasonable expectation for what your tangent space should look like if it sort of satisfies some basic reasonable problem. It should be an extension of the tangent space of your base by the tangent space of your p-adic neighbor. Identity algebra. Well, let me just point out, this thing here is a C vector space. A finite dimensional C vector space. And this thing here is a finite dimensional QP vector space. So whatever world we work in, it should allow for sort of interesting extensions between finite dimensional C vector spaces and finite dimensional QP vector spaces. And clearly you should think, like, depending sort of which field I choose for coefficients, like this is really growing with the field, whereas this is sort of always staying the same. Okay, good. So well, luckily I'm not just a geometer, I'm also a chaotic Hodge theorist, so I know which category to work with, which is Banach-Colmez spaces. So this is a category sort of that arises very naturally in the study of period rings and chaotic Hodge theory. It's sort of intimately related to sheaves on the Farquhar-Montaigne curve, as we'll see in a moment. And so it's sort of very natural from all its purposes, and but already sort of supernatural from the perspective of this talk, because these are sort of the tangent spaces that show up also in the Farg-Schulze criterion. So this is sort of they're also what you get from the Farg-Schulze Jacobian criterion. So those are sort of my first hint of what kind of thing I'm looking for. I'm looking for a Banach-Colmez space that gives me this kind of extension. Are there any questions while I erase?
Is there an easy way to understand? So your space, of course, is a limit of like torsors for a finite discrete group.
Uh-huh.
How is that being covered in the picture here? Like somehow, like how do you see that things should die when you go to finite level?
How do you see, sorry, what was the end of that question?
Like, so if you take your sequence up here, I'm just trying to understand. So somehow, if you go to a finite level, then you should just get an isomorphism on tangent spaces.
Yeah, so right. So some of the point is, the fibers have topologies. So the fibers, like if you sort of only go to finite level, the fibers sort of have a discrete topology. Whereas here, if you go all the way up to sort of infinite level, like your fibers sort of really now have a topology. But I mean, something you can't, and maybe I should say this, but like, this is another of those examples where you really can't see it as just like intrinsic structure of the diamond. Because if you take one of the fiber of this point S, like that fiber is just the profinite set GL2ZP, which sort of doesn't have like any intrinsic analytic structure as a diamond. It's just the profinite set, like it sheaves continuous functions that you can't see. Like so you need to, like if you have any hope of making this work, like you need to sort of think about, you know, think it's somehow you're equipping that fiber of some analytic structure, well, it's a p-adic Lie group. So sort of you have some guesses in your head probably about what that analytic structure should be in this case, but it's actually sort of a little bit hard to sort of make that turn into something that's going to give you the answer I want. So I'm not going to sort of do it that way. Did that answer your question?
Yeah, I mean, I was just more sort of wondering how you like get from that picture the fact that at finite level, like somehow, even though it's richer, you should be able to recover what's happening at the finite level from that sequence, I would imagine.
Yeah, well, so if you sort of quotient it out by like some open subgroup to get a finite level, well, on the level of Lie algebra, like on the level of tangent spaces, you should just be quotienting out by like the Lie algebra of that open subgroup, which is the same as the Lie algebra of the whole group. And when you take that quotient, you're just going to get the tangent space of S.
So, okay,
So that sort of recovers this idea.
and in that procedure, you again have to remember what, like how your space was built. You somehow can't do that intrinsically.
Yeah, exactly. And some others, I mean, well, and that's in that one, you first, there is some sense in which that's intrinsic because that quotient is a rigid analytic diamond, and sort of like that's a well-defined notion. Like anything that's in the essential image of a rigid analytic spaces, like that sort of makes sense. So in that quotient does have an intrinsic structure, but like in somehow an intrinsic analytic structure, like without sort of adding anything, but I mean somehow if you want to say the map from the infinite level thing to that thing is differentiable, I mean you sort of have to sort of given the tangent space at top. Did that answer your question?
I'll ask.
Closer? I'll take it. Okay. Yeah, okay, so here's the setup. I said this was a, hey, you can still see it here. This is supposed to be an example of something. Let me remind you what this is an example of. I mean, so this is sort of something I want to have a tangent space. I want my tangent space to look like this. The natural thing to say is, well, I have the Farg-Schulze-Jacobian criterion. Let me compute what that gives me. But that doesn't work because this is not sort of, there's no sort of obvious way to construct SE as sort of a moduli space of sections of something over the Farg function. So SE is not accessible by that's basic. So even though we're sort of doing all right, we sort of made some arguments to tell us we should get something that is a Banach-Colmez space, something that looks like it would also come from the Farg-Schulze-Jacobian criterion. I mean, we're not so good because there's no way to sort of access this space sort of via the Farg-Schulze-Jacobian. This one is actually a particularly nice example because for this one, you can actually, even though you can't sort of do it globally, you can access it by the Jacobian criterion on any residue disk. So this is accessible on any residue disk. Which sort of do not residue disk over, let's say, your classical point, for example, but in somehow these of course are not a cover of my adic space. So sort of knowing the answer on each of those sort of doesn't sort of, you can't just glue that to an answer. But let's just sort of talk about what happens in that case. So let's do a good reduction residue disk. Probably works also without good reduction, we can talk about it. So, well, in that case, you're either sort of an ordinary reduction disk or a super singular reduction disk. And so what does this look like? Well, you have to make some choices. But if you make some choices, you'll get an ordinary thing you can sort of identify with just the Serre-Tate space. Whoops, this is the infinite level version. Okay, so Serre-Tate space, I mean, this is just a disk with coordinate q, sort of an open disk of radius 1, sort of, where I sort of take the coordinates q minus 1, actually. This is an open disk around radius 1 around 1, and this is sort of the deformation space of an ordinary p-divisional group. And then here I sort of just take the trivializing cover for the Tate module. I get sort of the GL2CP thing. Good, and this is a hybrid square. So I have this, and then let me also posterity sort of draw this logarithm map.
Sorry, what is ST?
So ST is the Serre-Tate disk, so inside my finite level modular curve. STE is just a pullback of sort of this GL2C P torsor. In other words, it's like this has a universal P divisible group over it. This is the GL2C P torsor sort of trivializing as a height 2 P divisible group over it, sorry. And this is a GL2C P torsor trivializing a state module. Sort of ignoring the fact that I have like I can sort of reduce this torsor here. Okay, good. So this is and this STE you can compute this. The particle Jacobian criteria. Let me also sort of write down what happens over a super singular point. Well, now you have the Lubin tape disk. I won't sort of use a coordinate here. So this is again just sort of a disk of open disk of radius 1, residue disk at some smooth point. And then I sort of pull back the cover. That's neat. And then I have the Gross-Hopkins period map here at P1. There. Good. And this thing is also accessible by the partial to Jacobian criteria. What I mean is, let me say I base change to CP, that I can write down some smooth-adic space over the Fontaine curve for C flat, CP flat. Such that this is sort of realizes the modular space of sections of that thing. Then sort of if I follow through sort of statement of the Jacobian criterion, this would be some recipe to compute Banach-Colmez tangent spaces, and you can try to do this. And you'll get some answers. So this case is sort of treated by this case is sort of more general sort of basic PL cases were treated by Ivanov and Weinstein, and sort of not going to apply cohomological this Jacobian criterion. This one, you can actually, so once you know what the right answer, like once you know the right way to write the answer over here, which is what I'm about to tell you, you can sort of use the same method to do these ones too and sort of get the same kind of result. But anyway, you carry through this computation, which sort of, all these things, of course, have to be hiding somewhere in it, but it's sort of, like the finite level spaces sort of aren't really appearing in the definition via this thing, but you carry it through and you get some answer. And then you sort of squint at it and you try to write that answer the right way, and you sort of will end up getting sort of something that makes sense globally. So it's going to take a minute to sort of write down what that global answer is. But let me just highlight something here. Now, the reason I wrote down these two maps over here, because these are sort of period maps for the Hodge filtration. So in either case, you sort of have like, the Durand cohomology of your universal family of elliptic curves. Once you restrict to a residue disk, that has a basis of flat sections. And so you can sort of take the period map, sort of measuring the position of the Hodge filtration against that basis. And so you get sort of Hodge period map. Here's the logarithm. This is tau equals log Q. Here's the Gross-Hopkins period map. They're both examples of the messing period maps. And like, this sort of period map has nothing to do with this period map because there's sort of no way to sort of write down a basis of flat sections sort of that extends sort of from the ordinary locus to the supersingular locus. I mean, this is sort of the great bane of being a p-adic geometer. Sort of when you have an integrable connection, you don't get global flat sections sort of in any reasonable sense. So there's no way to sort of directly connect these, but sort of some miracle happens. It's not a miracle, it's sort of completely classical, but it's a miracle if you sort of set things up right and sort of make it sound like a miracle. The derivative of these maps, I mean, these are sort of completely intrinsic. This makes sense everywhere. And then for this deep hypothesis, this really is just a Pythagoras-Spencer map from tangent bundle of S to, well, if I pull back the tangent bundle of flags right along the period map, I mean, this period map is defined in sort of some terms of some filtration and sort of you're just moving along that filtration, you just sort of get Halms from this sort of quotient to the sub, or from the sub to the quotient rather. So this is Halms from omega E, so invariant differentials on E, which are the sub for the Hodge filtration that E. So you want to highlight here this sort of thing that should give you some hope that these answers you compute using the Jacobian criterion might stand some chance of possibly sort of giving you some answer you can just write down globally, even though it has nothing to do with the Jacobian criterion. is somehow exactly because of this miracle. It's because what we're going to do is we're going to write things using the Kodaira-Spencer map, and then once you do that, like you're sort of no longer like what you're writing can make sense more broadly than just one of these residue disks. So what I want to do is tell you how to do this. It's going to take a minute exactly to introduce some things about constructing Banach-Colmez spaces before I can tell you how the Kodaira-Spencer map shows up. But maybe it's the preview. I mean, so I told you what we're going to do. Sort of, it's going to work modular curve, but I mean, now you should be very optimistic because there's nothing special about the modular curve in terms of having a Kodaira-Spencer map, and that's going to work like anytime you sort of have a local system coming from cohomology, or more generally, anytime you have a Durand local system. And then, if you're following along closely with recent developments in chaotic Simpson theory and geometric stem theory and so on, then you will also know that the Kodaira-Spencer map has much more general incarnations beyond just Durand local systems. And so you sort of have some hope that this is actually going to work not just for Durand local systems, but for any sort of like p-adic retorsor. And in fact, this is the case. You'll sort of construct some tangent bundle for any p-adic retorsor there. And then what you'll start to ask yourself is, okay, like you start with the modular curve, we can relate it to like this very like well-reasoned Jacobian criterion from Farg-Schulze, and sort of, well, the modular curve, like, if I can write down some global answer that agrees on all these residue disks, like that's pretty good evidence that sort of this global answer has some meaning, but that's reasonable. But as you sort of depart further and further from that, you might sort of start to think the person standing in front of you is crazier and crazier. But so I probably won't, but and somehow what I wanted to do at the end of the talk, but you'll only have time for a few words about it, is sort of explain how to discover this. The recipe I'll give you, I explain that you can actually discover some completely different perspective that has nothing to do with the Farg-Schulze Jacobian criterion. Okay, good. So let's talk about how we actually sort of build this Banach-Colmez space. So we're going to have the tangent bundle right at that level modular curve. Well, maybe you know something about constructing Banach-Colmez spaces. Okay, and so P over QP is a perfectoid field. Tilt C flat. Well, then we have the Farg-Fontaine curve that we'll now sort of finally say something about. All right, so I'll just write it as X. Okay, so this is a scheme over QP, and it's basically in like a proper algebraic curve. But it's of infinite type. Not an algebraic curve over QP, but it somehow behaves like it in many ways. It's built from period rings. I mean, the idea sort of organizes sort of all the period rings and sort of a lot of fundamental results of p-adic Hodge theory in a very nice way. I already told you Banach-Colmez spaces sort of come up naturally in period rings, and sort of, well, Banach-Colmez spaces come up naturally from the study of coherent sheaves on the Farg-Fontaine curve as well, and that's sort of what we're going to exploit. I'm not going to define it or anything, but let me just sort of recall a few key points that illustrate sort of this property. So there's, well, if I take global sections of the vector sheaf, I just get QP. Mentioned this later. So if I take H1 of the structure sheaf, I actually just get 0. This property sort of says you're sort of not even better than a asymptotic or genus 0 curve, which is sort of very nice. We have sort of an ample bundle called O of 1, sort of some sort of completely canonical way to write it down. And you have this canonical C point, which I'm going to write as infinity. X to x, which, by the way, explains why I'm using E everywhere for like infinite level modular curves, because I wanted to sort of reserve infinity for this point on the Farquhar-Fontaine curve. Okay, so this is a canonical C point, and so how do these things all fit together? Well, we have natural embedding QP of 1, so there's compatible systems of P power roots of unity into global sections of O1. Maybe that's B. Where's the fuck? Up here? Could go down here, right? Got it. The P plus P equals P, that's the global sections of this ample line bundle. And so this is the thing that's then sort of a compatible system of P power roots of unity, where you think of that as an element of C flat, and you take log of its Teichmüller width. And so that's that embedding. If you don't know, don't worry about that if that's not familiar. I just wanted to sort of write it down. So we seem sketchy. And so I can use this to get sort of an exact sequence sort of presenting this point on the Farquhar-Fontaine curve. So this I have QP1. Well, since the global sections of O are QP, I can sort of tensor this one-dimensional QP vector space over QP with O. Then I just multiply together, sort of by sort of thinking of QP1 as sort of some set of sections of O1. So I get sort of a map from this to O1. And then that map's injective, and the quotient is just canonically identified with the sort of field C that supported this sort of point infinity. So this is a very fancy way to write down like the sort of more the map theta that we'll usually use in data codification. Okay, well, I just point out, like, if I took global sections of that sequence I just wrote down there, I would get sort of QP1 included to B plus Chris P equals P, and then the quotient is C. And then sort of there'd be no sort of third term because global set for H1 of O is 0. So that would sort of present B plus Chris P equals P sort of as an extension of a one-dimensional C vector space by a one-dimensional QP vector space. B plus Chris P equals P is sort of a Banach-Colmez space. And so you can sort of see that like using coherent sheaves and vector bundles on the Farquhar-Fontaine curve is going to be a really good way to get Banach-Colmez spaces. Like if I want to sort of get QP vector spaces, I just sort of take the QP vector space I want, I tensor with the structure sheaf. If I want to take get a C vector space, I just sort of take sort of the C vector space supported at infinity. And that will sort of, when I do global sections, give me that C vector space, but I can also get these sort of infinite extensions. And remember, I have and by the way, I guess I should say this. So I'm just going to use global sections to produce Banach-Colmez spaces, and this can be refined. It's refined by work of Arthur César, sort of give you an equivalence between sort of some category built of coherent sheaves and Banach-Colmez spaces, which is useful because you can actually really make computations completely on the Farquhar-Fontaine curve. And sort of, I won't sort of elide that point. Okay, I want to use this. I want to produce an extension of sort of the tangent space. The C vector space can be a tangent space at sort of some point of a finite level modular curve by the QP vector space in the algebra of GL2. So this is sort of what I want. So I'm going to sort of tensor the sequence above, sequence I wrote right here, with G minus 1. That means H with G by minus 1. Well, in the first term, I'm going to get 0 goes to now just G tensor O. So that's some vector bundle whose global sections will just give me G back. Then the next term I get E minus 1 tensor O1, and that's just what it is. And then in the next term I get this thing to support at this point infinity. Well, I take G and I base change to C. Okay, so I'm sort of halfway there. I've got sort of something in the current in sort of this part that when I take global sections is going to be give me G of QP, and there's a tree level nodes when I take H1. Like when I take global sections, H1 of this will still be 0, so I'm going to get an exact sequence of things. But over here I have too much. I have GC minus 1. That's not what I want. So I want to. So if I want to get something like this, I sort of need to. So to get my extension I'm interested in, I need to sort of pick a map from ESE ESS to DC minus 1 and pull back by sort of take the induced map from infinity star of this to infinity star of this, and I pull back the extension along that map. And I take global sections. And this really is sort of like a universal way to produce such an extension. So I'm sort of going to, any extension I get like this can be produced in this way. This problem I had before of sort of wanting to produce an extension of these vector spaces, now I've sort of produced a sort of slightly more tractable problem. I need to sort of give a map from the tangent space Fs to this Lie algebra, base change to C twisted by minus 1. Then I want to do it in sort of some very natural way. And somehow, in particular, I wanted to sort of like all this sort of vector bundle stuff in the Fourier curve. This sort of all spreads out sort of to a relative theory, and I want to get a tangent bundle then. And so it's sort of also sort of I should just sort of make a random choice at this point. I should see something intelligent here. And by sort of inspection of what I've said so far, I want to use the Kodaira-Spencer map at some point. So we just have to figure out sort of how to fit the Kodaira-Spencer map in here. So how do we do that? Well, let's see. Okay, so let me give you a different way to think about this GC. Well, this choice of my point SE, sort of on infinite level modular curve, this gave me a trivialization of the Tate module of sort of my sort of curve parameterized by sort of S. So this thing I can sort of think of it as sort of endomorphisms of the Tate module, sort of this with the curve and through its C. It's this is the CE squared by my explicit point. Now I have some stuff I can work with because inside of here, well, this sort of has some Hodge-Tate filtration on it. So this endomorphism ring has some endomorphism thing has some Hodge-Tate filtration on it, and it sort of has. I can take fill one of that. I'm going to get something inside of here. What is that thing? Well, let me sort of do this explicitly. So the Hodge-Tate filtration for the Tate module of this elliptic curve, well, the sub is the Lie algebra. And then the quotient is the very differentials on the dual elliptic curve, which and sort of nice. For techniques we can set something reasonable, it's good to sort of leave that dual in, even though it has some more picking. It's not like it's twisted, but anyway, it's not so important. Okay, and so then this is the Hodge-Tate filtration. So this is sort of fill one of this, and so fill one of the endomorphisms are just the things that sort of send this term to this term. So you sort of fill one of the endomorphisms is sort of exactly things that sort of project onto the quotient and then sort of map into the sum. So this L1 of this thing, this is just palm, omega E dual, to the one. Okay. Which, if I sort of pull out this H twist and then sort of pass the dual of both of these, so I flip them around, is going to be palms from omega E to the dual one.
Which
What's that?
from GK or kind of from
QB vector space and C vector space palms. But it's true. I mean, there's sort of some naturality here. And all I need is a C spec, and sort of to write something down, all I need is a C vector space palm. Okay, and so, well, I'm going to write it up here so I don't have to erase the board yet. So I want to get some map from the tangent space to GC minus 1. Well, this is going to be equal to, this contains omega E. The one, and I have a map here. So this is a Cadaris vector map. Okay. And so, I mean, so the magic is, okay, so I've sort of given you this map, tracing back. This map tells you how to construct sort of this sheaf on the Fourier-Fontaine curve, and then taking global sections, giving you the things I'm telling you should be like the Banach-Colmez tangent space at that point. So some of the miracle of this is if you sort of go back carefully and sort of compare on sort of each residue disk with sort of how you compute it with the Farber-Schulze-Jacobian criterion, you will get the same answer. So some of this answer sort of is the answer you get by the Jacobian criterion. Boom.
your GC, there is also the sign operator. Is it the same?
Yes, exactly. So let me say some things about that now. So as Pierre indicated, this is the sen operator, the geometric sen operator. So this is sort of good. The fact that it's the geometric sen operator sort of gives you a candidate generalization to any p-adic tensor. So any p-adic tensor has a geometric sen operator, which will exactly, so you'll have some Lie algebra, and you'll sort of the same argument will tell you you're looking for an extension to tangent one Lie algebra. The geometric sen operator is sort of exactly sort of a map like this. So if you sort of have these two thoughts at the same time, you can't sort of help but plug in the geometric sen operator here. And yes, that's good. There's some other interesting things that happen as well, though. And so I told you I want to sort of be able to differentiate maps. Here, in sort of some by construction, like my tangent space has a map to the tangent space of S, so the tangent space of the base for dynamic variety, and so my map rho is differentiable. And this is basically like I constructed my tangent space exactly so that the map rho will be differential and the orbit map will be different. Okay, those are differential. And what's not obvious from this is that the Hodge-Tate period map is differentiable. And to see it, say, in fact, sort of can compute also the Hodge-Tate. I mean, more generally, so in cohomology, you might sort of look at the setup where you have a Durand tensor. This is a order from P equal G. You around towards, or do you want sort of some extension? Your tangent bundles in some extension E times S by so the algebra of G by full dot. Yes. And you sort of construct this using the geometric set morphism, but it's actually sort of quite useful to sort of have some other computations of the geometric set morphism if you want to be able to do things like differentiate the Hodge-Tate period. So yeah, I'll just write down. I mean, here's one thing you can show. This geometric set operator. In this case. The geometric set operator is so it has a composition sort of lands over here, and this is sort of the target, like this is the tangent space of sort of the Hodge period map. So this is sort of the target of the Kodaira-Spencer map. Your geometric set operator is here, but you can sort of, this is a theorem, but okay, the geometric set operator you can prove is actually sort of canonical lift of the Kodaira-Spencer map. And actually, using that, you can sort of go back and you can connect everything sort of in sort of a weaker sort of spiritual way to the Jacobian criterion. I mean, the thing that should be accessible to Jacobian criterion is sort of local Shimura varieties and sort of the non-minuscule analogs. So if you have a works where you do have a basis of flat sections, and you basically you get a period map that says your tors are sort of, morally speaking, in some cases, should be pulled back from like a universal tors or over local Shimura variety. You can try and compare the answer we get in that case. And actually, that interpretation. I mean, so like, but you don't just have sort of a filtration period map. Like that filtration period map really lifts to a lattice period map, an affine Grassmannian. And that's exactly sort of what this is illustrating. Somehow, like the composed map is the derivative of the Hodge filtration period map, but this map here is the derivative of sort of your lattice period map. So this is a derivative of a map, the affine Grassmannian. And actually, sort of using Liu and Zhu's P-adic Riemann Hilbert, that interpretation works for any P-adic Lie tors that are sort of defined over a rigid analytic field. So somehow, like the map you're using to modify this geometric set morphism is in sort of in the same way that Kodaira-Spencer is the derivative of a filtration period map is the derivative of a lattice period map. So this sort of use a slightly stronger connection to the Jacobian criterion. Using sort of similar ideas, you can also sort of then sort of write down the derivative of the Hodge-Tate period map in sort of some completely explicit way here. But I think, okay, I'll say, I have one more minute, so I'll say one more thing. I mean, this talk was titled Differential Topology for Diamonds. I told you how to equip the structures, equip diamonds sort of with some differential structure, these sort of ones that happen naturally. And what can you do with this? Well, here I sort of talk about these P-adic Lie torsors and their tangent bundles, but sort of as soon as you have those, like it's clear how to compute also tangent bundles of quotients of P-adic Lie torsors. Moreover, like if you believe sort of tangent bundles describe the local structure in sort of some nebulous way of your diamond, then you should believe that your sort of diamond is preperfectoid exactly over the locus where your tangent bundle is sort of preperfectoid. And using that, you can sort of formulate a very nice conjecture about sort of preperfectoid locus, sort of the diamond that sort of can be sort of manufactured out of sort of natural operations. It tells you sort of exactly what's perfectoid, and this sort of generalizes conjecture 1 Esteban, sort of formulated in terms of the geometric set operator, just for like these P-adic Lie torsors. It sort of recovers sort of after the fact. Sort of, it's compatible with sort of known results about perfectoidness. I mean, somehow, okay, I can say more about that, but let me not. And you can also sort of formulate sort of much, I mean, maybe the coolest thing you could do with is you can now formulate sort of a notion of a submersion. Sort of, you can write down the derivatives and after that you can sort of talk about when something is submerged, then you should ask would sort of submersions be cohomologically smooth? And this would be a generalization of the Farner-Schulze criterion, in sort of some sense. All these things are sort of purely conjectural. And somehow, in some sense, I don't see any way to actually prove these things because there's a huge hole in this theory. And the huge hole is like, I haven't told you what an analytic structure is. I mean, somehow I've told you what the tangent bundles are, but I sort of just did it by sort of following my nose. So what you would really want is some theory of analytic structures on diamonds, and some sort of recipe for computing, some definition of a tangent bundle intrinsic to that theory, and then sort of, if this satisfied reasonable properties, these would be the tangent bundles. But somehow sort of without this, sort of, it doesn't seem clear that you can actually use this to prove anything. Of course, I mean, Juan and Louis have already sort of used geometric set theory to do like spectacular things. So of course you can use geometric set theory to prove things, but yeah, so there's some gap here. Well, maybe I'll stop there. So.
Questions? Yeah. So if you were to restrict this SE to a supersingular disk,
Yeah.
and then the Hausdorff period map establishes the restriction also as a torsor of a gentle upper half plane.
Yeah.
So you could use that torsor to form your tangent space.
Yes.
Are the resulting two tangent spaces canonically the same?
Yeah, so you'll get the same answer. Yeah, and so this is a good question. Is somehow because there's no sort of definition of analytic structure, so these are tangent bundles. I mean, you can worry that like you might have sort of two very natural things like this that are constructed in two completely different ways, sort of starting from natural operations for generating varieties. And I mean, somehow you want when either that thing has two different analytic structures, or you want your answer to agree. I mean, but for very nice things, it's sort of somehow better if your answers agree. It doesn't have so many analytic structures. And so, yeah, so like for basic local Shimura varieties, for example, like so there are always two presentations as p-adic Litors, so you can check sort of your answer agrees. It's not too bad. You get the same answer either way. And a fun one similar to this is if you just take a Banach-Colmez space itself, like take a vector bundle on a Fontaine curve of slopes between 0 and 1. I mean, typically there are like infinitely many different ways to construct this as a p-adic Lie torsor over originating variety, just by as you sort of construct as the universal cover of p-divisible groups or with matching slope filtration or with matching slopes. And sort of there are infinitely many different of those p-divisible groups, but all of those sort of give you the same answer. Then the answer you would expect, which is the Banach-Colmez space is its own tangent space, which is also sort of a Jacobian criterion one. So yeah, so there's but some of when you start making computations of these, you see that even though there's nothing built into the theory that guarantees you're going to get the same answer when you sort of do things different ways, it does seem to happen in sort of quite a few interesting cases where you sort of really get the same answer. So it's not, it sort of seems to be robust.
If you look at like model spaces of Stukas, do you get also tangent spaces that are not in the slope 0 and 1, but
yeah, so I mean, so for example, and if you look just the moduli space of Stuka with one paw, and so let me not sort of try and understand anything. So that's the limit of my knowledge. So it's okay. But if you look at moduli Stuka with one paw, so like these sort of non-minuscule infinite level local Shimura varieties, I mean, you can sort of basically, and you can write down what the answer is. You can write down like it's sort of completely clear sort of what the answer is because so you know what the like you can write down in a very simple way the tangent space, what the tangent space of like the affine Grassmannian should be, and then sort of there's a natural way to sort of extend that to a definition of what the tangent space of the of this infinite modulus space be, and then there are even sort of other ways to like justify that this is a good thing to do by sort of kind of ad hoc computations with the action of like G of BE on it. But you're not going to finish that. But so anyway, you can define these things, and one nice thing that's sort of I mean, something you do it and you do it in a way that's sort of compatible with sort of this idea I said that you interpret geometric set as sort of this lattice Kodaira-Spencer map, and sort of you're supposed to sort of be pulling back this universal torsor along sort of that sort of infinitesimal period map thing it's supposed to get. And so it's compatible with that. Yes. I don't know if that, hopefully that answered your question.
I got a bit lost in the, so you get point by point at Banach-Colmez space, or you get a family of Banach-Colmez spaces?
So at every point you get it, yeah, so good. So and for concreteness, I sort of wrote this sort of point by point. But in this geometric set morphism, for example, means now it's a global morphism, like it's not a point by point thing. And all this sort of constructions on the relative Fontaine curve is sort of made globally. And so after you get like a Banach-Colmez tangent bundle, not just I mean, you get sort of, let's say this way, you get sort of some diamond and QP vector spaces over like SE or sort of whatever, whose fiber at every point is a Banach-Colmez space. I mean, sort of the generally I set it up. I mean, like I don't know what the right. I don't know what the name. Yeah, I don't have a definition of Banach-Colmez space over an arbitrary diamond. So maybe you do. Maybe probably Arthur César does, but anyway, so fiber-wise, it is true, and whatever the definition is should be true. Yeah.
For example, when you have a Dirac torsor, is it important that the Zen operators are not zero, or?
No. So if the Zen operators are zero, then you're actually sort of in a very nice case, which is somehow you're in a case where you should expect that you do have a good Kähler theory. I mean, somehow, if you sort of take the dual of this map and sort of then take sort of its image, I mean, those should be sort of exacted differentials that are annihilated when you pull back to infinite level instead of this Kähler theory. And so basically, when this map is zero, well, the dual is also zero, and that says you sort of like after you should have a good Kähler theory at infinite level, and sort of you should have an isomorphic like an isomorphism tangent spaces sort of by this, just by the Kähler theory. So this like includes things like Iguza varieties, for example, sort of will give you such things. And this is quite nice, for example, when you're talking about growth peak messing period maps. So for example, when I said this thing, which is you don't sort of generally have sort of trivialized like flat sections over like globally. But if you start with a de Rham torsor and sort of assume like you're sort of a constant isoclinic vector bundle every point, then sort of the torsor of trivialization sort of like the modified bundle has zero as a Sen operator. And so you sort of get some global space where you actually sort of can talk about a growth peak messing period map, and sort of because of this, it should have like you can talk about differentiating it, and so you get sort of some global logic period map. So actually this is a useful case to consider. That is, sorry, I don't know if that answered your question. Okay, I'll take it.
So I'm a bit confused. So if I give you a triple GB mu or something like that, I look at the Shukka space.
Yeah.
Do you know a specific smooth projective variety that you can write over the Fontaine curve XS such that when you take the mapping space of it, it gives you the Shukka space?
No. So what I know is I know what the right, like I know if you do that, what the answer you should get will be for the tangent bundles, like sort of just easy way to express it. In the minuscule GLN case, there's sort of no problem to sort of actually do this. And then, I mean, yeah, in the Scholze-Weinstein paper, I think the presentation they give is a little bit like ad hoc, right? It's like but the Ivanov Weinstein paper works
sorry, not Weinstein Ivanov. So.
Yeah, but actually, I mean, well, there's sort of a natural sort of when we can talk about it afterwards. There's a natural thing to do to generalize it, but I mean, I'm sort of first year algebraic geometry is sort of my level. So it's like checking whether the thing you get is actually smooth is sort of not something that I sort of been able to do. But anyway, there's a way you can sort of try and approach it, sort of by a similar construction. And it's not so hard to basically you can use some Tanakian arguments to reduce the GLN case, and then sort of it's sort of clear what you should do to sort of try and extend it in the sort of arbitrary co-character GLN case, but it sort of requires some actual, at some point you'll have to do some actual computations. But somehow maybe the right thing is like it's not clear that one should do this, because somehow there are other reasons, there are clearly other reasons tangent spaces exist, and sort of have to do with geometric Sen theory, and sort of rather what one should try to do is sort of find some more general framework where tangent space exists, where sort of, there are like simpler ways you could, there are simpler ways you can compute that this is the right answer. The right answer I haven't told you. There are simpler ways you can compute that that is the right answer than sort of trying to shoehorn it into the Jacobian criterion. So it's not be, if that makes sense.
But your tangent space is not intrinsic to the space.
No, and somehow like implicit in all this is that when you start with original analytic variety, you have an analytic structure, and like GL2ZP, and this is a p-adic Lie group, like it has some analytic structure, and so in some sense you must be carrying out like all these constructions sort of should be carrying on around some notion of analytic structure with them, and then the tangent bundle should be sort of defined in sort of this like category of analytic diamonds, and so like yeah, so there are a lot of things I didn't say, but to make the connection with geometric sum theory, I mean, sort of you use the fact that there's natural inclusion of rigid analytic spaces into diamonds, but there's also a natural inclusion of like rigid analytic spaces over B plus gram mod T squared into diamonds, and sort of and sort of these are sort of all like the analytic structure is sort of just there in the diamond already. You don't need to do anything extra, and then. Like, for example, if you like include p-adic Lie groups, I mean, you need to sort of impose something else extra to have the analytic structure. And so all of these are actually sort of accessible in terms of like you have some locus over the Farg-Fontaine curve, you're taking some moduli space of sections over something over that locus, and sort of all. But then when you start doing these things where you mix the two, you sort of it's not like that's where it's sort of not clear what to do. And like so, like a simple thing you could try to do is sort of you say a p-adic Lie group, like I take a sheaf of locally analytic functions on it. You can sort of look like the minimal analytic structure that says, okay, like, so I know what the analytic structure on the basic original analytic variety is. I know what the analytic structure on each fiber is. And so that's what I want my analytic structure to be. And if you do that, you get exactly the sheaf of locally analytic functions that Lulé and Juan consider. But that doesn't give you this tangent bundle. I mean, in fact, what that gives you is when you sort of make this vector bundle on the Farg-Fontaine curve, you could sort of, instead of taking its global sections, you could take its fiber at infinity. And that's sort of the thing you get from looking at Taylor differentials for these locally analytic vectors. So it's some approximation. I said at the start I was going to try and say why that's a bad thing. Well, like one nice thing is sort of the structure of this tangent space. Like if you believe locally analytic functions are differentiable, the structure of this like the tangent space tells you the set operators have to annihilate locally analytic vectors. I mean somehow. So you could sort of forget sen operators. Like for a second, you could just say, like, let me suppose I do have tangent spaces, and let me say I can differentiate locally analytic functions. Well, if you just sort of make a Tor computation, sort of to take the fiber of this, you'll see immediately like sort of the map you get sort of from the Tor 1 terms, like gives you sort of some map in the tangent space of S, like to G, twisted into G, and whose image has to annihilate all locally analytic vectors. So somehow. There's reason to have this extra structure rather than just sort of that one. And so somehow, like the naive things you can do by sort of just like trying to combine the two analytic structures, like they don't sort of give you quite the right thing. I don't know if that answered.
I'm slightly confused. So do you have like a somewhat general theory, or is it just particular examples that you have, or? I'm slightly confused what.
Yeah. So what can you do? So it's not a general theory in the sense that I don't have sort of any like I don't have definitions for analytic structure, and so but somehow like you can write down sort of like what are like some basic first principles that should be satisfied. Like Lie torsors should be of this form, this extension, and then actually you should completely ignore and to set up things in more generally you should just. As a side result, you want to get compatibility with the Farg-Schulze, but sort of in saying what you want to be satisfied initially, you should completely ignore that. And what you can say, for example, for these p-adic Lie torsors, I mean, I believe the tangent space has a structure, and I believe the following map. B is sort of some rigid analytic group, and K is a p-adic Lie group sort of open inside of it. So if I believe, so this is a tangent space that's sort of given like in this extension structure, and I believe that this map is differentiable, Well, this thing is basically a twisted originality space, or pro-locally originality space on sort of the base. And I mean, this thing you can sort of compute very explicitly what its tangent space is, and sort of even sort of for sort of fairly naive definition of the tangent space. This thing you actually know what its tangent space is. And this is sort of how sort of geometric stem theory and Pierre Simpson sort of show up as sort of computing the tangent space of this thing. And then there's sort of exactly one possibility for the extension that's compatible with this map being differentiable. And so that sort of pins this down pretty tightly. Then you sort of make lots of computations for these things, for sort of starting with these things, and then quotients. You can sort of write down what the derivatives of period maps are supposed to be, and sort of somehow like affine Grassmannians, like there's no problem sort of saying what their tangent spaces are, and sort of you sort of know what the derivatives of period maps. So you get sort of lots of spaces and lots of derivatives. Sort of certain interesting things come this, and then you go back and you say, okay, like when I made all these computations, did I ever sort of run into contradictory statements? And you don't, and so it seems like it's pretty good, but I don't know, like it is like it's, in another sense it's just like an ad hoc jumble together. I mean,
so let's say so you have like some class of space where you have like a reasonable idea what the tangent space should be, and for example, if you take a G-torso over, it's still clear for the G-torso over that space.
exactly.
We sketch today what it should be. Is that some other idea? Or?
I mean, somehow you can do a lot sort of if you have that and you sort of you believe quotients by sort of like group actions by PID groups, originality groups like behave in the obvious way. And so if you believe those two things, like, I mean, then you have access to every diamond that I ever care about. I mean, somehow, probably not access to certain diamonds other people care about, but for me, that's sort of enough.
You get bungee.
And you can get sort of, I don't know. Yeah, and it's so
that's something I care about.
and another thing about this is, I mean, and you can sort of get things like this. And now, like, you can also believe that sort of if you have sort of something that's a V stack, I mean, you can sort of and you sort of have it presented though as a quotient of sort of something with a tangent space by like a Lee group action, then you can sort of just write down what this tangent space should be. And like this actually seems to contain interesting information. So for example, if you do this like for the Hodge-Tate period map at finite level, you get sort of a map from like an integral moderate curve to some V stacks, so like this P11 GL2 CP, and right now you have sort of a negative Banach-Colmez space as the tangent space of the thing on the right. But then you can be asked like if you can use this to show like this map is like smoothness properties of this map and sort of so like actually I mean sort of this kind of thing is sort of potentially within the realm. I mean, well, anything, and if there's no theory, everything is in the realm, but it is somehow in sort of an optimistic way.
Let's thank Sean again.